Here is a content page of our presentation today. Our presentation today is divided into three parts. First is introduction, second is modeling, and last is reflection. I'm the chief of the introduction part, and I'm going to give you a brief introduction. High-rise building, and it is a higher wall, and the frequency it will become bigger, and it will the safety of the building, and excessive frequency like this building. This building is built down because of an earthquake. Taiwan province is located earthquake zone. Earthquake there have the high frequency. There have the many hazardous conditions. There's events. Okay. Next, I will introduce the background information of Taipei 101. It was began in January 1998 and completed in December 31, 2004. The chief designer is Yuan.
Yeah, stay here.
Also for 2010 Shanghai World Expo. Like this picture, the whole building is 500 meters high, and it about 101 floors time about 101. On April 3, 2024, Hualien earthquakes in Taiwan province. Taipei 101 has successfully resisted a 7.3 magnitude earthquakes and survived completely. This is a chart of the top world's high-rise building. We can see that Taipei 101 is there. Okay, how does such a tall building resist an earthquake? The twin mass damper, we can call it TMD, plays a big role. This is a TMD. This, you can see, this is a huge steel ball, and its diameter is 5.5 meters, and it weighs about 660 tons. It was the world's largest damper. And at this picture, we can see that it's located between 86 and 92nd floors. Its main role is to help to decrease the vibration of Taipei 101 building, and as a result, it can decrease the vibration by 40%. Okay, and these are some research methods that are used by some predecessors. In order to better make about our research, we try a new method, the finite element method, to do our research. Okay. That's it. Let's welcome Riley.
I will introduce you our research process. Here are some applications we used from the analyses. Introduce modeling a function, setting density, and flex the platforms, solving the model, and observing the total deformation. Let's turn to our modeling process. We found that the building has observed a structure that is combined by different modules. So we decide to build it part by part. Firstly, we collected the size informations and built the base. The base is the shape of fractal. A fractal means a hybrid, a helmet cuts the upper part. And then we find the 27 floor to 91 floors are made by 8 same units. So we just build one of them. This unit is not a simple shape of the prism, but because its area of its bottom is smaller than the top, and its edge is also not a right angle, but a shape of a sawtooth. On the top of the building is a spire. We made it individually, but because it's quite complicated. with so much data in it. And its area of its floor is much smaller than the previous floors. And we also can find some of frustums, a shape of frustums in it, like this and this. Then we joined all the parts together and get our final model. We didn't add any details to it because on the one hand, we don't have enough time. And on the other hand, the computer is difficult to calculate if we make the model delicate. The next part is our outcomes. We choose different size of grids like 2, 5, 8, and 11 meters and get their results. We compared them and made a line chart. It reflects that when the mesh size become lower and the frequency is close to a certain value, even though the trend is not extinct in this chart. We used 8-meter grid as the example. We used 12 modes. It's the deformation situation of the mode 1. And we can see the maximum value is about 0.149 millimeters at the top. So the displacement is small. Because our building is approximate a central symmetry, so we combine each two modes, and this is the deformation of this the model under 3 different frequencies. So the displacement of the mode influenced by mode 1 or 2 is the smallest. And last is the dynamic image of these 3 models. Because the top is narrow, so it looks weird. Okay, that's all of my parts. Let's welcome Coco.
Yes, so it's my part about the reflection. And as we can see, both the chart and the diagram shows a result we get. And for this one, we search some documents and get these files. It is reported that the frequency in reality is 0.15 for F1, 0.43 for F2, and 0.78 for F3. And we can see from our chart, it was 0.15 for modes 1 and 2, 0.38 for modes 3 and 4, 0.79 for modes 5 and 6. So I think it is quite similar and comparable. So it is a good simulation of the model. And during the whole project, we can divide it into 3 parts: the preparation work, the modeling stuff, and the analysis. It was Bob and Riley did the preparation work, and Riley and I did it about simulating the models, and we all 3 joined the analysis. And actually, we encountered many difficulties through the whole process. It was actually the first time for us to both hear about and use the ANSYS. And it is, especially for me, the first time to simulate the models and to get everything and also to do the finite element analysis. So we learned a lot of new stuff and new knowledges. It was quite fruitful, I think. And for the second one is revolutions. Actually, we came up with many fantastic ideas. I shall explain it later in my presentation, but the time just limits us. So we hope we can just further expand it in maybe the 1 month later, and to get something more useful and more creative in August. And here is actually the course of our whole project. At the very beginning, we made one simple and fluid model. It was only it was only imitates the shape of the Taipei 101 building. And for the stage number 2, we came up with the idea of the mass damper, and we just make the upper side of the building into a higher density to simulate this situation. However, it didn't work that well, so we changed into a real ball and use either the string or the damper to connect it. However, it requires, if we want to achieve that circumstance, we need to add some damping on the ball. So, but the time just limits us. It requires much more time beyond 2 weeks. So we just come back to the very first model and to finish this report. And as I mentioned before, there are 4 main parts we want to further investigate in the future. In my opinion, the most important one is about the damping, because the damping, we have now already the models of the whole structure, but we only need to do is to learn about the damping knowledge and get the board can served as a damper. And I think on the basement of the damping, we can add the earthquake strike and the swale on the structure. We can use the sine function to replace the earthquake strike to test the vibration of displacement of the building, and also because in my opinion, Taiwan province is surrounded by sea, and the soil there is quite humid. So I think the soil there might make the tower to incline, and I think it is a good point to talk about. And in that case, we can prevent such circumstance to happen. And for the 4th point is about pillar or the frame, because we all know that the Taipei 101 building is made up of four huge steel pillars to support the whole structure. And I think once we can make the structure simulated, and we can maybe the vibration of the building will change a lot. And at the last part, I want to make some compliments. I think our group is quite hard learning, collaborative, and positive. We learned a lot of new knowledges and new skills during the whole process. We encountered many difficulties, but we just all face it together and just get some results. And also, I'm here to thanks to the Professor Boha, because you offered us about the discussion about the key points in our research, and also the suggestions for the further research. And also, I want to thanks to the TAs, because it was actually them that teach us how to make the models and how to do the finite element analysis. They also help us to get the slides and reports much more better. So that's all for our project of the Taipei 101 building. Thank you very much.
We are the Hohai University group, and today we will introduce this building named Bank of Chinatown. Our groups consist of 3 students, of which Edward, me, is in charge of modeling, and Calvin, he is in charge of data processing, and Lucy is in the charge of making the PPT and write the report. And we will proceed to report our research this time. The effects of vibration damage are mainly composed of 2 aspects, which are resonance damage and fatigue damage. One of the famous case of resonance damage is in 1849 on the River Main in Angers, Western France. When the soldier in the parade passed the bridge over the river, the bridge suddenly broke, causing 266 people to fall into the water and die. While fatigue damage is mainly manifested in airplane parts and ship parts. Based on this, This paper investigates the self-vibration characteristics of structures and achieve the goals of design optimization, vibration control, and structure health detection of structure to provide safer and more reliable structures to peoples. Shibuya will give you adoration and life. So this object of study is a Bank of Chinatown. He was designed and built by the A.O. Mingpei. And the construction time began in 1982 until the end of 1989. The overall height of the building is 325 meters plus the height of the top two posts, totaling 316.7 meters, and covers an area of about 6,700. So in order to build a simple solid model, this model was divided into 5 parts, namely the foundation and 4 triangular tiles when it was built. And the following figure shows the diagram and the model building process.
Oh, okay. For the model analyze, we need to get the material parameters here. So the left figure here shows the volume of the dimensional data of the tower 1, which can be divided into 2 parts here. The first one is the triangular prism, and the second part is the triangular pyramid. So we can calculate the volume here. We can use the area of the bottom, multiply the height here. And the second part, we use the area of the bottom, multiply the height and multiply a third. Then we plus 2 parts of this structure. We can get the total volume of the tower 1. And then for the same calculation method, we can get the volume of the tower 1, tower 2, tower 3, tower 4, and the foundation here. Then we plus them together, we can get the total volume. For the search date, we can get the external load. It's 19.8 billion kilogram, and which can be divided with the total volume here. We can get the density, which was used for the model analyze. The density here is 250 kilogram per cubic meters. The second material parameter is the elastic modulus. The figure here shows the calculation of the moment of the inertia. For the idea of the equivalent of the structure, the solid structure and the frame structure, we can calculate the fluctuation. According to the idea of the equivalent fluctuation rigidity, the elastic modulus of the solid structure and the frame structure are equated. And after the calculation, we can get the elastic modulus, which was used for the solid structure, is 1.33 G Pascal, and the elastic modulus used for the frame structure model analysis is 30 G Pascal. And then this is the solid structure and the frame structure that we created using ANSYS. Here, after the model analyze, we can get the first mode of vibration, and this is the second mode of vibration, and the third, the fourth. the fifth and the sixth. In this study, we only investigated the first six mode here. Then we divided the solid structure and the frame structure into meshes with different accuracy for model analyze, and the frequencies of each order of the obtained model are plotted in the following figure, which shows that the improvement of the meshes here, the convergence of each order of the frequency is faster.
Okay. Okay. Compared with the solid and the frame model, we can find that the first two mode of frequency is similar, and but however, after the three mode of the Oh, okay. Yeah. Starting from the third vibration mode, disparities between the two calculation gradually increase. And okay. To investigate the stability of the building, we use the history data of Alessandro wave from the Imperial Valley Irrigation District as seismic input into the ANSYS, and we analyze its acceleration, and we integrate it, and we get the velocity, and we only input the velocity into the ANSYS. And two prompts are our inserts as the location shown in the diagram. The displacement as probe 1 is denoted as U1, and as probe 2 we as a U2. The formula for interstory drift angle is given below. Yeah. We conducted analyze using both elastic and elastoplastic models, resulting in the graphic shows in here. From the graphs, we can it is evident that the maximum interstory angle drift angle for the plastic structure is slightly larger than that the elastic structure, but remains within the safe range, indicating the model's stability and safety. Finally, we present the following three conclusions. The higher the mesh accuracy, the faster the convergence of the computation. There is a difference between the simulation of the solid structure and the frame structure, and the appropriate model should be selected in comparison with the actual results. And the maximum storage drift is 4 milli for -3. Thank you.
So hello everyone, today we are going to talk about finite element analysis of resonance in the structural design of Eiffel Tower. Please let me introduce our group. So I'm Eric.
I'm James. I'm Frank.
So this is how we distribute our work. So I'm basically responsible for the model setup, doing all the simulation, running all the plots, making the presentation, and do a small portion of the report writing. James, he mainly focused on report writing, and he also helped us to prepare the presentation. Frank also made the first draft of the presentation, and he spent a lot of efforts in material selection process.
And we start target is Eiffel Tower, a famous attraction that attracts lots of tourists and a global and as a global cultural icon of France and a broadcast tower for radio and television signals. And the tower is 3,324 meters high and weight 10,100 tons. Its main material is wrought iron. Because this main material is why we interested in Eiffel Tower, because Eiffel Tower is built in 1887. At that time, most of buildings were made of stone or wood. As the first iron building, our team think it's have great research value. And our team also wondering why the Eiffel Tower could last so long and so well for nearly 200 years. Because there are two lakes in front of on the foot of the tower, which leads very unstable foundations, and the wrought iron itself is easily to get the rain and the water corrosion. What kind of structure means and structure made this tower so well is also our curiosity and research direction. And we also look at other iron buildings like Tokyo Tower in Las Vegas and in Shenzhen. These buildings were mainly built at 20th century or 21st centuries. We surprisingly found that their structure are very similar to the Eiffel Tower. And the Eiffel Tower can be divided into three parts. The first part has four massive pillars, each supported by a concrete foundation. And the second part also has four legs inward and converge as they rise. And the third part has platform, features restaurant and exhibition space without any waiting structure. And this is our team objective. We first create 1-to-1 3D models of the Eiffel Tower, and we test our model tower with different frequencies to get some data. And we use our data to compare with other papers to test our data, to test our authenticity of the model. And we found the reason speculated for the Eiffel Tower, the longevity through resonance frequency. And the last, we hope our result can be applied to other similar structures with geometric scaling. Thank you. Let's welcome the.
So as James just mentioned, a geometric scaling is a really important part of our research because there are many similar structures with exactly the same layout but different heights. So by using this fundamental equation of natural frequency, we can apply a small factor to it and calculate all the frequency as long as we know our model frequency. So this is our model, and this is the real Eiffel Tower. Our model scale is 1-to-1, which is exactly the same to Eiffel Tower. However, there are several features that are removed. For example, the antenna is removed because it is made up of a different material and it's really thin. Of course, restaurants, exhibition spaces, and observation decks are not featured in our model because it would be too complicated for the computer to do all the simulations. So this is how we select our material. Also, as James just mentioned before, the whole tower is made exclusively of wrought iron, which makes our simulation even more simple. So wrought iron is a iron alloy with a very low carbon content, similar to today's low carbon steel. And however, it is actually a precursor to the construction steel, because at that time, steel is not that widely used in France. And one of the interesting facts about wrought iron is it actually have a really big thermal expansion coefficient. As you can see, wrought iron was mainly used in those old structures. And this table is all the coefficients we use, because in SolidWorks, it do have this material already embedded in the software, so we just use the whole material. And I also made an engineering drawing of our model with all the important dimensions. So this is the front view, this is the top view, this is the bottom view, and this is the trimetric view. And as you can see, our model actually is really precise and accurate. It features all the small stresses and beams in the real Eiffel Tower. And I'm pretty confidently to say that our error in dimension is actually smaller than 5 meters. Okay, and another feature I would like to discuss more is the base of Eiffel Tower. So this base is actually made up of four squares, and each with a 30-meter dimension. So with that being said, I'm going to dive more deep into the boundary conditions. So we can see from this real-life picture, the base of Eiffel Tower is actually 4 concrete blocks. To represent that in our model and simulation, we just made a base with the same dimension and apply a fixed boundary condition to our model. So here are our results. We have do 3 trials of an analysis with 3 different mesh qualities. One is coarse mesh, one is moderate mesh, and one is fine mesh. And for a better mesh quality, the node number also increases. As you can see, it goes from 57,000 to 100,000. And the element number increases simultaneously. And this is actually the mesh result picture of the Eiffel Tower we use. It is a little different from ANSYS, but I don't know if you guys can see, there are actually little triangles and tetrahedrons inside this picture, and this is only the coarse mesh. And the coarse mesh took us about 4 minutes to run, and the moderate mesh took us about 8 minutes to run, and the fine mesh took us about 16 minutes to run. So with more element and node number, significantly more computational power was needed. So here are our FEA results. We can see our first mode shape and second mode shape have really similar frequencies, which is about 0.66 Hertz. Our third and fourth mode also have really similar frequencies, around 1.92 Hertz. And our fifth mode have a frequency of 3.13 Hertz. And our first and second mode, the displacement only focus on the upper part of the Eiffel Tower, and they're just simple axis bending. One is around the x-axis, one is in the y-axis. But as the mode number increases, the middle part of the Eiffel Tower also start to move, also for the fourth mode. But for our fifth mode, like the whole tower is start to have displacement all throughout its body. Its legs also start to move. And by the way, this is just in real life, it is not that obvious for us to see those kind of displacement. SolidWorks actually applies a visual enhancement method to make the displacement more obvious to the audiences. And this is our results in numbers. So we have all 3 trials of 3 mode shapes and with 3 mesh qualities. So we made a box plot to summarize all the results. And we can see at mode number 1 and 2, the results are actually pretty much the same, regardless of the mesh quality. But as the mode shape number increases, there is actually a slightly increasing trend of the frequency as the model have a better mesh quality. And as we learn in our class, a higher mesh quality represents a more precise results. And from our analysis, we can see that even though we increase the mesh quality a lot, our results still stays pretty much the same, which again tells us that our results is accurate and precise.
Thank you for Eric. Now, please let me introduce our conclusion and discussion. Our group decided the tower into 3 parts, and just as Eric have shown in the picture. These 5 pictures. Have you ever known the vibration mode? Our group has 3 modes. This is the mode 1 and mode 2. This is the mode 1 and mode 2. The first order vibration. And this is the second order vibration. This is the third mode vibration. Just like this 5 picture. So we can find that in the mode 1 and mode 2, the third part is the highest part, makes the most deformation. And in the mode 3 and mode 4, the second part makes the most. And from mode 1 to mode 4, the first part is the basement and seldom makes some deformation. However, in the mode 5, the first part also makes some deformation. And here is the results. You can see the blue line in the table is the result from our analysis, and the orange one in the table is the result from another researcher. We can find the tendency of the 2 lines is similar to each other. However, there is some difference between the 2 lines. And here, the deviation is 0.33. After discussion, we find that the deviation mainly comes from the parameter of the material we have set. And although there is some deviation, the deviation is quite small in the whole structure, so it can be ignored. And next step, we plan to add some other force in condition to our models, such as the wind tower, the earthquake, and other things. As it's all known to us, France is a place where seldom confronted with extreme earthquake. It seems that analyze the Eiffel Tower is impractical. However, I believe that if we can apply our model to some other place where the earthquake is active, is very meaningful, such as the sky tree in Tokyo. That's all.
Any questions?